Okay. So I'm going to draw a line, something that's approximately 10 centimeters. Sure. And that represents the distance from the sun to the nearest star. Okay? How far along your line in carbon diameters would be the distance from sun to Earth? And what is the distance from sun to Earth? That would be a given, has to be given. So this is 10 centimeters is the same as 4.22 light years. Does anybody have, so I don't have to go fishing for it, the distance from sun to Earth? Drawing not to scale. Oh, I see, thank you. 1.49. So is that a long distance, 1.49 times 10 to the 8th from Earth to sun? Is that a long distance? It depends, right? Of course it's a long distance, right? When you think about walking across campus. But what about going to the nearest star? It's going to be a long distance or a short distance? Incredibly short, right? Very, very short, okay? So we need to figure out, so first we want to figure out how many centimeters this is, right? On our segment. So let's figure out how many centimeters that is. Well, 4.22 light years, so we need, light years is, we need to figure out how many kilometers that is. How many kilometers is 4.22 light years? How many kilometers is 4.22 light years? All right. Call it A. So what? 4.22 light years is the distance that light could travel in a year. So this is how far distance light could travel in 4.22 years. So we need the speed of light. And with the speed of light, we could get how many kilometers light travels in 4.22 years, okay? So this is the number of kilometers light travels in 4.22 years. I'm just going to call it A for time's sake. I would assume, based on doing the other problems, I think you can do that, right? I think you can do that. You get the number of kilometers light travels in 4.22 years. So how now am I going to find out how many centimeters along my line is Earth from sun? Well, we could say how many of that number of kilometers fit into the whole number of kilometers. So how many groups of 1.149 times 10 to the 8th would fit into A? Well, that would be A divided by 1.49 times 10 to the 8th. And what would that give me? That'd give me the number of sun to Earth lengths that makes up sun to the nearest star length, right? That'd be a number of distances to the sun that would make up the distance from the sun to the nearest star. And so what are we going to do? Then if this whole thing is like 10 centimeters, then we want that fraction of 10, right? So we want, no, that's all right. So that's the number of them. So what fraction of this is the whole length would be 1 over that, right? So yeah, let's start with 1.49 times 10 to the 8th over A is a different way to think about this. That's the fraction that the distance to Earth is for the sun of the distance from the sun to the nearest star. So I like that better. And then we know that fraction of this length, we're going to multiply it by 10 to get that fraction of 10 centimeters. So that will give us how many centimeters it is along our line from sun to Earth. Okay, and now we know what the diameter of a carbon atom is. How long are in carbon diameters? Okay, so that's we know how long it is in centimeters now. So in carbon diameters, we have it in centimeters, and we want it in these little teeny diameters. Then we're going to do what? How many of these fit into this many centimeters? Is that right? So we're going to take that whole thing and divide by the 2.2 times 10 to the minus 8. Does it make sense? How many of these lengths would make up this length in centimeters? So that would be how many diameters it would be from the sun to the Earth. So once you find that number of kilometers in 4.22 light years, 1.49 times 10 to the 8th over that, times 10 gives us that in centimeters, divide by the width of one carbon length, and we get that length in the number of carbon atom diameters. Does it make sense? Do you follow? Okay, so we'll just stop there on that one. Questions or discussion on that? Again, there's other ways to approach it. So this is just the way that I saw it made the most sense to me. But there are other ways to approach these. We want to try to kind of avoid is just unit analysis canceling units, because it becomes kind of mindless. This really these kinds of calculations really force us to think about multiplication and division and their meanings. Okay. All right. Last chance. Questions? Yeah, please.
So in the top we did A divided by 1.4.
Yeah, I kind of, and I abandoned that.
Could we keep going that route?
Yeah, you
and
probably
do
could somehow.
10 divided by whatever the answer that gives us?
Yeah,
Okay.
Yeah, 10 divided by, what was that? That was that length in centimeters?
Yeah, the 10 centimeters divided by the answer in the top part.
Yep.
A divided by 1.4.
Yeah, that will also work too.
Okay.
My brain just went more easily to this other way, but yes, that will also work too, and there's a very good explanation for it. Yeah. Other questions? Okay. All right, so I've got this little animation here, and I'm going to assign to the value z, the use z is equal to, it's a variable, it's going to take on your used smartphone memory space in gigabytes. So we'll talk more about variables in more in detail later, but just very simply, variables vary. They take on different values at different moments. We want to get out of the mindset that a variable, it has a certain value and I got to solve for it. Okay, sometimes, so that's true, but overarching meaning for variables is they take on many values in a context. Right? So you know, as you're going through life with your smartphone, your use memory is changing all the time. So we want to say z takes on the current amount of use space. Okay? So now, and here's an illustration of that. And I want you to just look at the red bar there. It's a red bar extending from 0, starting out to 6, and then increasing to 7. So it's starting at 0. And so what could be the meaning of the red bar? Very simply, what could the red bar be representing? Z, right? So hopefully you're seeing that's just a representative of Z. Okay, so Yeah, so this red bar starting from 0 and extending out to some ending point on the right is just representing Z, the current amount of smartphone memory that's used. Okay, so what about the blue bar? So what about the blue bar? What could that be representing? If the red bar, the length of the red bar represents Z, then what about the length of the blue bar? So why don't you just take 20 seconds to introduce yourself to your new workmate at your table. No one gets left out. And talk about what the length of the blue bar might represent. Go. Okay, and so you did some reading about constant rate of change, and so thinking about maybe in the reading, just so very simply, what could the length of the blue bar represent? What's that? Distance. Yeah.
Is that a data a certain app took up when you installed it?
Okay. So what is that relative to Z? So yeah, so maybe we're installing an app, and it's gonna, right? In this case, that app is gonna eat up how many gigabytes? One. So we had 6 before. It's gonna eat up one more, and now we have 7 used up. So what could that, just generically, could that blue bar represent?
The Z, or well, the D.
Okay. Yeah. What were you gonna say? Yeah, the change in Z, right? So this is generically, I'm using that blue bar to represent a change in Z. So if you said that, good for you. So, and the notation for that is, from the book? DZ. All right, not delta. Delta we're saving for later, okay? No deltas for the next couple weeks. We'll let you know when delta comes into play. So we're just going to, DZ is generically going to mean a change. A change, and so DZ is a change in Z. Or a change in your used smartphone memory space. Okay, so looking at your sheet now. We'll do the first one together. What you're going to do is, so you see for each one of these items, there's ZI, which stands for Z initial, ZF, which stands for Z final, and a DZ. Okay, so let me illustrate using this. So it says at first 3 gigabytes were used. You downloaded a file that was no, at the end 5, sorry. At the end it was 5, is that what it said? Is this representative of that first question? Okay, so what you're going to do in all these questions is 2 of those variables will be known. You're going to put those in, and then the third one you can find. So in this case, do we know Z initial? It is 3. Your use space starts at 3. Do we know Z final? Yes, 5. So in this case, DZ is the one that's not given, immediately known. All right, and what is DZ? Okay, clearly it's 2. And so now you're coming up with the formula that you did to do that. Okay, some of you are laughing. When stuff gets hard and you're not able to recognize this in a hard ball of stuff flying everywhere in front of you, you're going to be lost. So that's why we're going to go slow. It's going to be really easy, okay? Start easy, because we really have to have this like the back of our hand. So you're going to write down the formula to compute DZ. So what you would write in that box is DZ equals something, because DZ was the unknown in that first case. So DZ equals, you're going to finish the formula. Okay, and then, so, any questions on number 1? Does it make sense? All right, so you're gonna do numbers 2 and 3 only. Do numbers 2 and 3 only, and then we'll regroup. Don't go beyond number 3. I will go ahead and represent number 2 next here on the screen. Always when we put you to work, take time to think and work by yourself, but always we encourage you to then share answers, ask questions with those around you, okay? Here, I'll put number 2 up there. Okay. Here's the animation for number 2. Here's the animation for number 2. Again, identify the knowns, identify the unknown, and then you're going to write a formula for the unknown one. So it might not be DZ in the next one, okay? So do number 2 and confirm with the person next to you. Never turn on the label. So for number 2, make sure that what you're seeing up there matches with what you came up with. Okay, I'm going to go ahead and set it for number 3. Shoot. Get that wrong. Sorry. That's all right. Go ahead and discuss numbers 1 through 3. Discuss numbers 1 through 3. Make sure you got it. Okay, well, let's start with number 3 and work backwards since I'm showing number 3. So number 3, Z final or Z initial is? 0.3. Z final is? 1.2, which makes DZ? 0.9. So the unknown was? DZ. How is DZ computed? DZ equals? Z final minus Z initial. The final value of the final amount minus the initial amount of Z will give you the change in Z. This should make perfect sense. We're going really slow so that it makes perfect sense. There's no doubt about why you would subtract Z final minus Z initial to get the change in Z. That's basically a definition of subtraction, right? That's one way to think about subtraction. When you subtract two numbers, you get the change between them. Okay? And remember, it's z final minus z initial. Z final minus z initial. Okay, number 2. Z initial is? Z final is? That's the our unknown, or you can calculate it, and then dz is 3.5. So the unknown is z final. How do you find z final given z initial and the change in z? Okay. You start with what you, so the final value of a quantity is the initial value plus the change. It should make perfect sense. It should make perfect sense. What were those values again?
4.4 was the initial.
And 3.5?
The 3.5 was DZ.
Okay, here we go. So, if we start with 4.4 and we make a change of 3.5, how are we going to get the final value? You're just going to add the length of the red bar, z, plus the length of the blue bar, dz. That will give you z final, or 7.9. So, by the end, then our new value of z is 7.9, the final value of z. Okay, let's just do, so tell the person next to you, take 30 seconds. What's the difference between a value of z and a value of dz? Take 30 seconds, tell the person next to you, and take turns. Both do it. What's the difference between a value of z and a value of dz? Okay, and then just go ahead and move on to numbers 4 and 5. Just do 4 and 5. Go. Same thing as 1 through 3. 4 and 5. Just 4 and 5, and then when you're ready to compare, share, talk, do it. I'm showing number 4. I'm showing number 4 on the screen. Okay, number 4. Z initial is 8.8. Z final is 4.7. Unknown is the change in Z, dz. What is the change in Z? Negative 4.1. What's the formula that gets that? dz equals? Did you make a new formula? It's the same formula, right? Z final minus Z initial. If Z final is less than Z initial, then you get a negative change. A negative change indicates what about Z? Decrease, reduction, right? So this is nice because we can use negative and positive on a change to indicate increase or decrease. So when dz is negative, we have the same formula. We get a negative value. That means Z decreased, and Z final was less than Z initial. Okay, and then what about for number 5? We erased a file that was 1 gigabyte. That means what variable is what value? dz is negative 1. Do we need a new formula for Z final? No. Same formula still works. Z final equals Z initial plus the change in Z, and if that's negative, we're going down, right? So Z final will be less than Z initial because we took Z initial plus a negative value to get a lower value. Questions on this? Questions on this? So these two ideas, principles, two essential principles we just came up with. Given a variable x, the change in x, or dx, is what? Final value of x minus initial value of x. Yes, memorize it, but it should make 100% make perfect sense that you would take the final value of a variable minus the initial to get the change. That's what subtraction is, or that's one way to think about subtraction. Other principle. Given a variable y, you write it. So what am I gonna write up there on the screen? You write it. Everyone think to themselves. What's our other principle that we came up with there? You write it. Okay. Someone back here. What am I gonna unveil here about given a variable y? dy equals y final minus y initial. Is that different? That's the same thing. That's just a different letter. It's the same thing. Yeah, so it doesn't matter what letter we pick here. A, B, C, X, Y. So I already covered that one. So on the other side, what am I going to say? Somebody new. I'm going to bring a roster on Tuesday, and I'm calling you by name. Yes, ma'am.
Y final equals y initial plus dy.
That's right. So the final value of y, if you were to calculate a final value of y, that would be the initial value of y plus the change in y. Okay, so yes, write them down. Yes, memorize them, but it should make perfect sense to you. And these two little two little principles they're gonna pop up over and over and over again as we develop this very complicated thing of calculus. So bringing calculus down to some of its core principles, these are two of them. So, and in a month, it's going to be really complicated and really hairy in terms of formulas and variables all over the place. But it's going to boil down to of all the things it boils down to, these will be two of them. Okay. Here's another thing that's going to be really important. So we've said, so now we're talking about if it's dy, we say you could compute dy as y final minus y initial, right? I'm just changing the letter again. It's the same principle. The change in a quantity, final value of the quantity minus the initial. But if y changes along with x in some relationship, then dy can be determined a different way using dx. That's what we want to talk about now. Okay, so here's a different way to come up with dy. If dy is changing along with, or y is changing along with something else, x. So then this is going to be our, this is going to be the way we think about and understand constant rate of change. Okay, constant rate of change is about how two quantities change together, a very specific way that two quantities change together. So using dx to determine dy. So here's an example. You're using your car's cruise control on a straight, flat, smooth highway, and you set it to 70 miles per hour. Okay, 70 miles per hour. That's a value of in this scenario. That's a constant rate of change. That's a constant rate of change. Okay. So what is that? What's the meaning of that? So that number 70. What does it mean? What's the meaning of 70 miles per hour? Tell the person next to you in 20 seconds. Go. What does this number 70 mean as a constant rate of change? Okay, so in a nutshell, what would you say the meaning of 70 miles per hour is? How would you find that? Yeah, right there. Okay, but what is that? So what does the number 70 mean? Yeah, so yes, it's the constant rate of change of distance, but what does the number 70 mean? Yes, sir. Okay, did you say every hour you go 70 miles? Is that a meaning for that? For every additional hour means an additional 70 miles traveled. What do you think about that? Is that all there is to it? Okay, so what we want to emphasize today is that this is a very, very narrow meaning of 70 miles per hour. And you all know that it's a narrow meaning. You just don't know that you know. Here's how you know. Because why? Because you also know how far you go in 2 hours. How far do you go in 2 hours? 140 miles, right? You knew that. You also knew how far you go in 5 hours. 350 miles. You also know how far you go in half an hour. And you also know how far you go in a tenth of an hour. You know any more than that? We could go on all day, right? We could go on all day. 70 miles per hour means a whole lot more than just you go 70 miles in an hour. What? Actually, we know how far you go in any amount of time, right? And so if x is time elapsed, we call dx a change in time. So given any change in time, dx, how far do you go? How far do you go? Given any change in time. So what were you doing in every one of those examples that I gave you? Right. How did you get the number of miles traveled? You multiplied by 70, right? So given any change in time, the change in distance is 70 times that change in time. That's an infinitely broader meaning for 70 miles per hour because it tells us an infinite number of things, right? As opposed to just the one fact that you go 70 miles in an hour. You actually know how far you go in any change in time. Okay? So for any change in time, this is what the 70 means. What the meaning of the 70 is embodied in this mathematical statement. For any change in time, the change in distance is 70 times that change in time. You knew that, but you didn't know you knew it, right? So again, our meaning for 70 miles per hour is this formula. Or in other words, given any change in time, the change in distance is 70 times as much as that change in time. Which is, these are all examples of that. She just rattled off, no problem to me, right? So this is a formalized formalized way of describing every single example that we could think of. Given a change in time, to get the change in miles, multiply by 70. Make sense? Super important. You're filling up your gas tank and the gas costs $2 per gallon. What's the meaning of $2 per gallon? Yes, it's a constant rate of change. So what does that constant rate of change of $2 per gallon mean? Tell the person next to you. Go. Okay, how about every additional gallon means $2 more in cost? How about that?
It's too narrow.
True? True. But very, not. It's just true. It's not technically true. It's just true, right? That every gallon you add to your gas tank is going to cost you $2 more. That's absolutely true. All right, but again, narrow, right? Narrow. We know so much more than that, right? What do we know? Given any, ladies, I expect A's on the first test. All right, what's that? Given any number of gallons, what? The change in cost is 2 times that number of gallons, right? If you put 10 more gallons in your tank, you all know how much more you're going to have to pay. How much more? Say it. 20. You have to multiply 10 by 2. If you put a half more gallon, or let's see, 5 more gallons in your tank, how much more is it going to cost you? 10. Okay? For any change in the number of gallons, the change in cost is 2 times that change in the number of gallons. That's the meaning of $2 per gallon. And that meaning is exemplified in this equation. Okay, any questions? Seems easy. But we've done this many semesters in a row. Students have trouble. We get to these situations and these problems. If this isn't at your fingertips, at the ready, when you're tackling problems, then you're going to struggle. You're going to really struggle. So that's why we're really going slow and emphasizing it. Okay, so here an example: a store sells make your own snack mix gifts. The box costs $B, and the snack mix costs $2.75 per pound, which means what? What does the $2.75 per pound mean? Tell the person next to you. Go. Okay, what does $2.75 per pound mean? Somebody knew. Somebody knew. Come on, who's got it? Don't be shy. He said the change in cost will be $2.75 or 2.75 times the change in the number of pounds. Exactly right. So any additional number of pounds will increase the cost of the gift by 2.75 times that additional number of pounds. Okay, so when you come to real-world situations in this course, you need to change your mindset from, okay, what formula do I use? What do I plug in to get what answer? To start off by really understanding the situation and applying variables and defining your situation in terms of variables. So I'm going to give you the variables: x, y, dx, dy, and m. And you're going to write out phrases or verbalize phrases of which each of those are. One-word definitions will not cut it. That will not be specific enough. You got to be specific. Use units, so the person you're telling it to knows exactly what you mean by each of those variables. Okay, so take a minute or two and say what is x, what is y, what is dx, what is dy, and what is m in this situation. These are written phrases that are describing the meaning of those variables or those quantities. Okay, go. Okay, compare with the person next to you if you haven't already. See if you got the same thing. Again, explicit phrases, written out phrases that specifically define what each of these quantities are. So I'm going to give you the first one. So then we're all on the same page. X is the number of pounds of mix in the gift. Number of pounds of mix in the gift. Go from there. Go. Oh, shoot. How did that work? Okay. Okay, so X number of pounds. What is Y? Okay, total cost of the gift with X pounds in it, right? With X pounds in it. Okay, dx. Okay, a change in number of pounds. It's a change in the number of pounds. Okay, dy would then be change in the cost. M is our constant rate of change, 2.75. Okay, questions on that? So this is the way you should always approach real-world problems, and most of the course is going to be real-world problems. Okay, most of what we do, whenever you start, it's about identifying quantities, changing quantities with variables, so that we can build equations, right? So identify them with good explicit descriptions. Yeah. Is B included in Y? Yes, it's the cost of the gift, right? So it's the cost of the whole gift, right? But what about dy? Does that have to do with B? Right, okay. Okay, so write an equation. So suppose you're gonna add 1.4 more pounds, okay? 1.4 more pounds. How much does the cost of the gift go up? Figure it out. So you're gonna add 1.4 more pounds of mix. How much does the price go up? Should make sense. What do you do? Yeah, you're just going to take every pound is 2.75. Additional pound is 2.75. So you take 2.75 times 1.4, and what'd you get? 3.85? Is that the cost of the gift? So- how much the gift went up in price? How much it went up in price? How much it changed? So now I want you to write an equation using two or more of the variables over there that computes the change in cost for the change in the number of pounds bought. In other words, represent what you the calculation you just did with variables. Represent the calculation you just did with variables. So that 3.85, we found what? What variable did we find when we found the 3.85? You should be thinking dy, the increase in the cost. And how did we find it? We took the cost per pound times the additional number of pounds. So we're going to take that constant rate, m, times dx, which was the 1.4. So when you did that calculation, 2.75 times 1.4 equals 3.85, this is what you were really applying in a formalized way. That the change in cost was the constant rate, or the price per pound, times the additional number of pounds. We're going to be eating, drinking, sleeping, breathing this the next month. Okay, homework will be posted by 4 o'clock today on Blackboard, by 4 today.